Hey guys, so I would like to quickly just make a video similarly to what I did back for 3.2. Just a clarification video. Um, may be self-explanatory at this point, but just to show you why it makes sense that psi tilde of k, right, the wave function expressed in the momentum basis, right, why this should be equal to ck, right? And I showed this back in the other clarification video, that if you were to graph, right, this would be the k-axis, and this would, and now we're graphing the value of psi tilde of k, right? If you were to graph this, and it looked something like this, right, what this would tell you is, for example, that we have a very high probability of having this momentum, right, or this wave number, which corresponds to a certain momentum, h bar, times that, right? We have our times this point. We have a good probability of having this momentum. We have the next highest around here, right? It's for the wave number, right? And this makes sense that if we're writing out the state of the particle, right, what we're doing is we're just writing out these coefficients that tell us how likely that particle is to have that certain wave number, right? And of course it can go into the negatives where these would just be moving in the opposite direction because, as you know, momentum is a vector, right? And it doesn't have to be symmetric. It could be most likely moving to the right this way, but have some probability of moving to the left, right? So yeah, that's all I want to do, just clarify that. And you can really do that with any other continuous quantity, right? And the coefficients themselves, this tells you a lot about how important these coefficients are, right? They tell you how likely you are to have a certain value of an observable, or it kind of weighs out how likely you are. In this case, it's the norm squared will give you probability density in k-space, right? Right, that's important to remember. To get the probability density, and to get the probability, you have to integrate this function norm squared. But yeah, so this just kind of reminds you how important those coefficients are, but also what is the state of the particle telling you? Well, it's giving you a probability distribution in a way, right? Or something you can easily get the probability distribution from. To tell you how likely you are to have this momentum or this momentum, right? And if we're in a discrete basis, right, it's kind of like writing the state of the particle like this, right? C1 phi1 plus C2 phi2, right? These coefficients really are what tell you what the state of the particle is, right? If I just write out, this is 1 over, let's see, it would be 1/2, I believe. No, sorry, it would be like this. If I had like 2/5 psi1, or 3/5 psi1 phi1 plus 4/5 phi2, right? This is normalized, right? You have a let's see, 9 over 25, so 36% chance of having psi1, and a 60, or having the value q1 for your observable, and 64% chance of having the value q2, and that's the state of the particle, right? If these were like the white and the black states, right, that tells you what the state of the particle is. So these coefficients are very important, and so it turns out we can write the state of the particle psi tilde of k. It's just that function of the coefficients.